after having familiarized ourselves with the different types of standard signals one has to deal with normally in system analysis, let us now introduce ourselves to some elementary system concepts which will be found useful later on in this course. Generally, when we are talking about the analysis of systems, we would like to assess the dynamic performance of the systems, and in this context it would be useful for us to remind ourselves of what a steady state of a system means and what the transient state of a system means. When the variables of a system or a network are either constant DC values or are regularly repeating periodic functions of time, then the system is said to be under steady state conditions. Under sinusoidal circuit theory, you deal with systems under steady state conditions where all the voltages and currents are periodic functions of time which are sinusoidal in character. Similarly, in DC circuits you deal with steady state conditions when all the voltages and currents are constant. So, once again the system is said to be under steady state when the signals characterizing the system are either constants or regular periodic functions of time. The best way to define the transient state of a system is to say that a system is in a transient state when it is not under steady state. There is no other simpler way of doing that. So, in general, on account of a switching process, you open a switch or close a switch, or some system parameter suddenly changes, then the network transits from one steady state to another steady state, and the intervening period in the transition between one steady state to another steady state is referred to as the transient period, and it is a study of the transients which forms the central theme of the analysis of networks and systems that we are going to take up. Strictly speaking, most of the transients take infinite time to die out, but in practice, as far as the engineering approximations are concerned, within a relatively short time, which is 3 or 4 times the time constants involved, we can assume the transients to decay to negligible proportions. Let me take an example to illustrate this idea. Suppose I have a 10 volts DC source connected to an RC circuit with an initial capacitor voltage of 4 volts, and I would like to find out how the capacitor voltage behaves for time t equals 0 onwards if the switch is closed at t equals 0. Now, the capacitor voltage Vc to start with is 4 volts, ultimately it will reach a voltage of 10 volts, it gets charged to this 10 volts. Therefore, the capacitor voltage, the steady state voltage of the capacitor is 10, that is the steady state voltage of the capacitor. But at the time of closure of the switch, the capacitor voltage is 4 volts, and there is no reason for that voltage to change because there is a resistance here and that absorbs any shock that comes in between. This is 10 volts, this is 4 volts, this 6 volts is dropped across the resistance. So, initially the value of the capacitor voltage must remain as 4 volts. Therefore, you have a transient term which is minus 6, and from your elementary knowledge of transient analysis there will be T over CR. So, this is an exponential term which decays with time. Therefore, Vc of t is 10 minus 6 e to the power of minus t CR. CR is the time constant of the circuit. This is the steady state part and this is the transient part. So, in going from one steady state to another steady state, in going from 4 volt steady state to a 10 volt steady state, you have a transient arising. So, the capacitor voltage can be, this is 10 volts, this is Vc steady state, new steady state of course, originally it was 4 volts, and then you have a transient term which is a initial amplitude minus 6 and decays like this. So, this is the transient component of the capacitor voltage. The sum of these two will give rise to this curve like this. This is the actual capacitor voltage. This is the actual capacitor voltage. So, you recognize in this process a steady state value and the transient part, and the transient component arises because the old steady state does not match the new steady state, and therefore, there is a transient which bridges this gap. In order to solve for these transients, you have different approaches available. The classical differential equation approach is the most fundamental method, but it is somewhat complicated, but nevertheless, since one has is a fundamental approach, because most of the equations of the network are written in terms of differential equations. Therefore, it is a fundamental approach, and since you have studied differential equations in your mathematics courses, it would be convenient for us to see how the differential equation approach can be used to study transients in networks of this type. So, we will illustrate this, introduce this idea through an example, and then later on we will show that some of these difficulties associated with the solution of transients through differential equations approach can be overcome using operational methods like Laplace transform methods at a later point in the course. But to get a feel for the advantages of Laplace transforms, we must know what the difficulties are in the differential equation approach. So, let us take an example. Let us consider this particular circuit to illustrate the differential equation approach. We have an inductor and capacitor in the circuit, and the inductor and capacitor provides the initial conditions that are necessary to solve the problem, and normally the initial conditions are given pertaining to the situation before a closure of a switch. So, let us say IL0 minus before the closure of the switch is 0 amperes, and the capacitor voltage before the closure of the switch is also 0. And let us also say that the source voltage is 12 volts DC. To solve for this particular solution, to solve for this particular circuit, let us take the loop equation approach. We have two currents I1 and I2 in the two loops. We write down the differential equations pertaining to the two loop currents to start with, and then let us say that in this particular problem you are interested in finding out I1. Find I1 of t for t greater than 0. So, this is the solution. So, let me write down the differential equations for the two loops. You have for the first loop R1 I1 plus L times d by dt of I1 minus I2 must be equal to Vs, and this can be written as R1 plus L d derivative operator operating on I1, because derivative operator d is equivalent to di1 by dt, capital D times I1 is di1 by dt, minus LD operating on I2 equals Vs. That is the first equation, where by definition d by definition is d upon dt. Similarly, d squared by definition is the second derivative of the particular quantity. Okay. Now, for the second loop, suppose you take the voltage drops in the direction of the loop current I2, you have R2 times I2 1 over CD, that is the integral of the current I2 divided by C, that is the voltage Vc, plus d by dt, L times d by dt of I2 minus I1 is the voltage drop across the inductance in this direction. So, if you write that respective terms, you get R2 plus 1 over CD plus LD operating on I2, that is equal to 0, because this 1 over CD indicates the integral of I2 dt. 1 over CD I2 means 1 over C integral I2 dt. That is the voltage across the capacitor. So, that is what we are having. Now, we are interested in solving for I1. Therefore, we have to eliminate I2. If there are purely algebraic equations, we would have multiplied by suitable factors and we have eliminated I2. The same thing can be done here also, recognizing that these are derivative, these are operator functions, but we can manipulate them in the same way as the algebraic factors. So, you multiply this factor by LD and this factor by R2 plus 1 over CD plus LD and eliminate I2 in the process. And substituting numerical values, you get for this particular circuit, eliminating I2, we have 6D squared plus 5D plus 1 operating on I1 equals 2D squared plus D plus 1 operating on Vs. This is the final differential equation that you have connecting the source voltage and the response quantity I1 that you are interested in. In system representation, we can put this as an input quantity Vs and the desired output I1 is represented by this fashion. This is characteristic of the type of differential equation we will get in all these problems. So, this can be put in this fashion: an operator function Fd operating on I1 equals another operator function Gd operating on Vs, whereas this is the input, this is the output. The output and input are connected by a differential operators of this type. Fd operating on I1 will be Gd operating on Vs. So, this is characteristic of all single input single output systems. For the solution for this, in the classical differential equation approach, is done in two parts: the complementary function solution this is part of the solution. So, I1 complementary will consist of two terms depending upon the roots of the auxiliary equations. So, the auxiliary equation we have here is 6m squared plus 5m plus 1 equals 0. This is the 6d squared plus 5d plus 1 is 0. You substitute, you use m for d, and this is what we get as auxiliary equation, and the values, the solution for this will be m equals minus half and minus 1/3. So, the complementary part of the solution will have an arbitrary constant a multiplied by e to the power of minus t by 2 plus another arbitrary constant b e multiplied by minus t by 3. So, this is the complementary part of the solution, which is familiar to you through your courses in this elementary course on solution of differential equations. Now, we have something to say about this. Now, this complementary solution, whatever you are getting, is also termed the force-free solution or the natural response of the system. Natural response. Because this portion of the response, the characteristic of this response, this t by 2 and t by 3 minus t by 3 will remain there no matter what source you take, what forcing function you take. Whatever forcing function you take, that portion will remain the same. Therefore, this is inherent to the system and this is the natural response, and this equation is called the characteristic equation. Now, it is called the characteristic equation because of the fact that no matter what variable you wish to solve for in the circuit, whether you want to solve for I1 or I2 or the capacitor voltage or the inductor voltage, whatever you want to do, the characteristic equation will remain the same. This will you will get, that means this f of d will you get the same f of d no matter what you take as the response quantity, and so this is something which is characteristic to the system and is independent of the forcing function. That is why it is called characteristic equation. And the roots of the characteristic equation are the natural frequencies minus half and minus 1/3 are the natural frequencies of the system. So, the complex frequencies present in this particular signal are minus half and minus 1/3. They happen to be real in this case. but in terms of the general concept of complex frequencies, these are the two values -half and -1/3. They are the complex frequencies present in the system. They are called the natural frequencies because they are inherent to the system and they arise irrespective of the forcing function that you are having. So, this is the complementary function solution which is obtained from solving the characteristic equation and auxiliary equation. We have to of course solve for A and B because they are arbitrary constant, they depend upon the initial conditions. But before we proceed further, we need to have the particular integral solution. The particular integral solution from your elementary study of differential equations will be obtained as g of d by f of d operating on the forcing function Vs. This is an operator function. We know that if Vs is of the form say a e to the power of alpha t, then the particular integral solution is obtained as g of alpha divided by f of alpha a e to the power of alpha t. That is, the operator d is replaced by simply the factor alpha in the exponent. That is how it goes. Now, in our case, Vs equals 12 volts DC, therefore, we can take 12 e to the power of 0 times t, alpha is 0. Therefore, the particular integral solution I1 particular integral solution is G0 divided by F0 multiplied by 12. If you substitute d equals 0 in this equation, you have this F0 is 1 and G0 is 1, therefore, this is 12. Particular integral solution is 12 volts, 12 amperes. Now, this is also called, whatever solution you get here, this is also called forced response, because this is the response which depends upon the particular input that you are having. This is the Vs forces this kind of response through the differential equation, and the complex frequencies present in the forced response will be exactly the complex frequencies that are present in VFS. If VFS has a single complex frequency alpha, then this also will have, the solution also will have that complex frequency alpha. If this has a complex frequency S, this will have a complex frequency S. If this has a variety of complex frequencies S1, S2, S3, 4, then I1 particular will also have all those complex frequencies. So, the forced part of the solution has the same complex frequencies that are present in the input waveform, whereas the complementary solution will have complex frequencies which are inherent to the system, they are called the natural frequencies. Okay. Now, we have got the particular integral solution as well as the complementary function solution. So, the total solution is I1 equals a e to the power of minus t upon 2 plus b e to the power of minus t upon 3 plus 12. This is the natural part, the natural response, this is the forced response. Now that we have got the total solution, the form of the total solution, we have to evaluate these arbitrary constants A and B, and for that we need to know the initial conditions. From the initial conditions, we should be able to find out A and B. We need two conditions. So, it is convenient in these situations, there were two conditions on I1, we need to find out I1 0 plus and the derivative of I1 evaluated at 0 plus, di1 by dt evaluated at 0 plus. You can think of any two equivalent conditions, any two conditions, independent conditions, but these come naturally and they are convenient to calculate. I1 0 plus I1 prime 0 plus. Now, how do we go about it? It is the initial conditions of the reactive elements which provide a link between the situation before the switching operation and after the switching operation. They form the bridge between the conditions in the circuit before the switching takes place and after the switching takes place. So, it is ultimately related to IL0 and Vc0. We assume that Vc0 plus is the same as Vc0 minus. Normally, the capacitor voltage is continuous unless there are impulse currents, which we will see later. Normally, we can assume this to be true, and there is no reason for the capacitor voltage to change suddenly as far as this circuit is concerned, and IL0 plus is the same as IL0 minus. So, we can say that Vc0 plus is also 0 volts, and IL0 plus, which is really I1 0 plus minus I2 0 plus, that is IL equals I1 minus I2, this is also 0. So, this is the information that is given to us, and from this information we should be able to manufacture the values of I1 0 plus and I1 prime 0 plus. How do we do that? Now, let us see. At t equals 0 plus, you have this 12 volt source and you have R1 and R2. The current in the capacitor inductor is 0, therefore, that is almost an open circuit, and the capacitor is a short circuit because the voltage across the capacitor is 0. So, you have R1 1 ohm, R2 2 ohms. So, the current I1 here is 12 divided by 1 plus 2 3 ohms, therefore, I1 0 plus is 12 upon 3, that is 4 amperes. That is the initial value of the current, 12 upon 1 plus 2 4 amperes. Now, how about the derivative of the current at t equals 0 plus? Now, to do that we have to do some kind of manipulation. From this circuit we can see that Vs equals I1 R1 plus I2 R2 plus Vc. This voltage equals I1 R1 plus I2 R2 plus Vc for t greater than 0. Let us take the derivative of this. This is of course 12 volts. All the time this is 12 for t greater than 0. Take the derivative of this constant is 0, R1 is 1 ohm, therefore, I1 prime 0 plus 0 does not matter at any time t, this is I1 plus, and then this is I2 plus I2 prime times R2, which is 2 ohms, plus dVc dt. That is what you are having, I1 plus I1 prime plus 2 I2 prime plus dVc dt, R1 being 1 ohm and R2 being 2 ohms, right. Now, this is true for all values of time greater than 0. At t equals 0 plus, this is 0, I1 prime 0 plus 2 times I2 prime 0 plus what is the value of dVc dt at t equals 0 plus? The current in the circuit, current in C here at t equals 0 plus is 4 amperes. This is 4 amperes. So, what does it mean? That C dVc dt, that is the current in the circuit at t equals 0 plus, equals 4. This is I2 0 plus. I2 0 plus is the same as I1 0 plus. From this we observe that dVc dt at t equals 0 plus, dVc dt is 0 plus 4 divided by 2, which is equal to 2. C equals half a farad, half a farad. So, C equals half a farad, therefore, this is equal to 8 volts per second. Therefore, this substitute dVc by dt is 8. So, this will lead me a result I1 prime 0 plus 2 I2 prime 0 plus equals minus 8. Now, we need to have another equation. This is not enough. Now, we need to have another equation in I1 0 plus, I1 prime 0 plus and I2 prime 0 plus. What is the voltage across the inductor? VL equals L times di1 by dt plus di2 by dt minus di2 by dt. That is what we are having. At t equals 0 plus, what is the value of the voltage across the inductor? This is equal to VL 0 plus. What is the value of the voltage across the inductor at 0 plus? 2 ohms and a current I1 of 4 amperes, therefore 8 volts, the capacitor voltage is 0. So, at t equals 0 plus, this is 8 volts. L equals 4 henries and this is I1 plus I1 prime 0 plus I2 prime 0 plus. So, you have another equation from this I1 prime 0 plus minus, I am sorry, this minus I1 prime 0 plus minus I2 prime 0 plus equals 2. So, you have two equations. One is I1 prime 0 plus 2 I2 prime 0 plus is minus 8. The other equation says I1 prime 0 plus minus I2 prime 0 plus is 2, and the solution for this, from these two you get I1 prime 0 plus as minus 4 upon 3 amperes per second. So, you have I1 0 plus is 4 amperes, I1 0 prime is minus 4 by 3 amperes per second. So, you use this information to solve for A and B. So, to solve for A and B, we use I1 0 plus equals 4 amperes and I1 prime 0 plus equals minus 4 by 3 amperes per second. You substitute these values in this expression straight away, this value, and take the derivative of this and time put t equals 0 plus and substitute this value. You solve for A and B, you will get a solution A equals 24, B equals minus 32, and finally you get the solution as I1 of t equals 24 e to the power of minus t upon 2 minus 32 e to the power of minus t upon 3 plus 12, and this is a solution valid for t greater than 0. That is the final solution. So, let us see what we can gather from through the example. In the differential equation approach, you have two parts of the solution, the complementary part of the solution and the particular integral part of the solution. The complementary part of the solution is obtained through the solution of the auxiliary equation or also what is called the characteristic equation. And this characteristic equation is independent of the particular response quantity which you are choosing. It depends upon the system as such, the composition of the system and the various elements. And the natural frequency, the frequencies that are present in the complementary solution are what are termed the natural frequencies. They are in general complex. In our particular case, it may have been real, but in general complex. So, these complex frequencies present in the source free response of the complementary solution are called the natural frequencies. This is characteristic of the system, it does not depend upon the particular forcing function. On the other hand, the particular integral solution is what is called the forced response part of the solution, and it has all the frequencies which are present in the excitation function or the input function. The sum of these will be the total solution, and in solving for this we need to have information about the initial conditions of the quantity which you are going to solve for. In mathematics, generally when you solve the differential equation, these initial conditions for the region of interest are given to you, but in problems of this type we do not have those initial conditions given to you straight away on a platter. What you are given is, in a circuit like this, some initial conditions pertaining to the regime before the switching operation. From this you must find out the new initial conditions appropriate to t equals 0 plus pertaining to the particular quantity which you are interested, whereas the initial conditions are given in terms of the capacitor voltage and inductor currents. So, this requires a lot of manipulation, as we have seen, and this is really one of the troublesome aspects of the classical approach of the classical differential equation approach to the solution of the problems, because if you have imagine that you have an nth order differential equation, here luckily we have only 2 reactive elements. Suppose you have got 5 reactive elements, the differential equation would have been of 5th order, and you need to have 5 initial conditions pertaining to any quantity which you have to solve for, not only the initial value but the first 4 derivatives. Even for first derivative we had so much trouble. You can imagine the type of trouble which we had if we had to find out the initial value of the 5th derivative. So, this is really a problem. So, in the classical solution you need to find out the initial conditions appropriate to the particular quantity which you want to solve for, and this requires a considerable amount of manipulation. In this particular example what we have taken, we assume the capacitor voltages and the inductor currents are continuous, which is normally the case, but there may arise situations where the capacitor voltages have to jump from one value to another, from 0 minus to 0 plus it may have to undergo a jump, and similarly the inductor currents may have to have a jump from 0 minus value to 0 plus value. As we have seen in an example, when a battery is connected to an uncharged capacitor, immediately the voltage has to jump, an impulse current has to exist. So, we may even in the evaluation of the initial conditions, it may not be always necessary that Vc0 minus is equal to Vc0 plus, and IL0 minus may not necessarily be equal to IL0 plus. So, such cases also merit our attention. In the next lecture we will take an example or two of where such special initial conditions occur, and then continue with our discussion of some of the elementary concepts that are needed for the analysis of systems, which we will make use of in our later work.